Hello, everyone. Welcome to pre-lecture 9. This is going to be for our lecture on Tuesday, continuing with chapter 12, kinetics. So just a review from last class that one of the things we're concerned about in kinetics is not only how fast reaction goes, but how it actually happens. And so the three things that must occur for a reaction to happen are that molecules must physically collide with a sufficient enough energy to break bonds between reactants, and that will then allow the formation of new bonds in the products. And they also must collide in the correct spatial orientation. And so just a reminder that all three of those criteria must be met in order for a chemical reaction to occur. We also talked about the frequency factor that is made up of orientation factor and a frequency of collisions. So reminder that our orientation factor there is going to be the most important one for our class. Essentially is a number between 0 and 1 that represents the fraction of collisions that have the correct orientation. So the closer we are to 1, the more likely our reaction is to occur based purely on orientation, right? We also talked about activation energy. So that is the energy required to kind of go up the hill, as it were, between our reactants to get to the top of our transition state before we then have a release of energy in order to form our products. Okay, and our transition states, or rather our activation energy is very important because without it, our reactants would just automatically turn into products. We wouldn't have any barrier between them. So reactants would automatically become products, okay? All right, so in classic Gen Chem 2 fashion, we talk about our activation energy. We of course want to find a way to quantify that. And so we can do that using an equation called the Arrhenius equation that actually provides us a little bit more quantitative backing for what our rate constant K actually comes from in a molecular sense. So our rate constant K is going to be equal to A, which is our frequency factor that we discussed. E is the constant E, and then E sub A is our activation energy. R is the ideal gas constant with units of energy, and then T is our temperature in Kelvin, okay? So if we if we determine the rate of a reaction, aka K, at multiple temperatures, then we can also make a linear form of the Arrhenius equation that can be used to determine the activation energy. And so this is the kind of y equals mx plus b form, where y is going to be the natural log of our rate constant, is equal to the negative activation energy over R times 1 times T, plus the natural log of A, which is, hopefully you remember, our orientation factor. We can actually have a 2-point equation form as well. So if we measure the rate at different temperatures, then we can use this 2-point form, which of course looks similar to our Clausius-Clapeyron reaction, but instead of pressures, we're using rate constants, K, right? And then temperatures. And this is something that we're actually going to do in experiment 13 in lab. So I would recommend learning this, as you will be seeing it over the next couple of weeks in lab. All right, so shifting gears a little bit from talking about activation energy to reaction mechanisms. And so oftentimes when a chemical reaction occurs, there are going to be 2 or more steps to this. And so this process of steps we call a reaction mechanism or a reaction pathway. And it basically breaks every step of our chemical reaction down. So an example that we might have of an overall reaction are the decomposition of ozone. So ozone is O3, and we could say it's 2 elementary steps. Our first breaking apart O3 into O2 gas and just oxygen as an atom. That oxygen atom reacts with a second equivalent of ozone to form 2 moles of O2. And so that would mean that our overall reaction is 2O3 yields 3O2. However, we know that that actually takes place over 2 steps. Also, this O that's formed, the pure atom oxygen, appears first as a product and then as a reactant. And so because of that, we call it an intermediate. It's not counted in our overall reaction because it is both produced and consumed as part of our elementary steps. Okay, and that's again what we define as an intermediate. So we have this reaction where we have N2 dimerizing and eventually decomposing into nitrogen gas and oxygen gas. If you were to look at this, I could ask you, and I probably will ask you on a quiz, something like, what is the overall reaction that occurs? What intermediates might be present during these elementary steps, and also to write a rate law for step 2. And so I want you to think about that. We're actually going to go over this one in class, and so I would recommend working on it before then, but if not, we will at least be able to cover it in class, okay? Right, another part of reaction mechanisms, another vocab term that we can talk about is their molecularity. This relates to the number of reactants of species that are present. And so if we think about this in terms of rate law, we could say that for a unimolecular reaction, our rate is only going to be dependent on one substance, thus the uni in unimolecular. So A turns into products. If we have a bimolecular reaction, we can have 2 moles of A makes products, or A plus B. So we could say our rate is equal to a rate constant times A squared, or K is K times A times B. That would also represent a bimolecular reaction. And then, of course, a termolecular reaction is when we have 3 species involved in our reactants. And so that's an example of a termolecular reaction right there. Right, and again, this is just another way we can describe reactions is in terms of their molecularity. All right. Within our elementary steps, we can also talk about what is rate limiting or rate determining. And so this step may be an apt metaphor for us in Southern California. Say we have a 4-lane highway and it closes down to just 1 lane due to an accident or construction, so that only 1 car can get through at a time. And so if we think about that in terms of a chemical reaction, we would at certain temperatures above 225 degrees Celsius have this as a rate law, but below that temperature, we will have a rate law where K is just equal to NO squared. And because we have different rate laws at different temperatures, that suggests a 2-step mechanism. And so this is the mechanism we could propose shown here, where our first step might be slow. So we could say that our bottleneck or our 1-lane highway might occur in our first step. If that's the case, then we look at our reactants and we have 2 moles of NO2. And so this should actually say, instead of NO, it should say NO2. Sorry for the confusion there. Forgot a 2 right in that spot. And then if it was above 225 degrees Celsius, then our second step would become our slow one, or at least slower. And then our second step would become rate determining, and then our rate law would reflect that. Okay. And so, like I just said, the rate law for our overall reaction will be determined by the slowest elementary step. Okay. And we're going to talk more about that in class, how we might go about determining that, but I hope that was a good introduction. If you have any questions, of course, please feel free to let me know. Otherwise, I will see you in class. Take care.